This is packet 6 and 7 combined for energy part 1 and energy part 2. Let's focus on energy part 1. Here we're going to discuss definitions for potential energy, kinetic energy, something we call heat, and temperature, as well as memorize and apply temperature conversions for fluorine, Celsius, and Kelvin. So part 1 is pretty straightforward. We have very simple definitions. Please don't think too much into this. Potential energy refers to stored energy. So water behind a dam is potential energy. If I were to sit there and draw a hill with a boulder on top, then there is a high amount of potential energy as it can roll down the hill and scare the tar out of people that are on the bottom. Chemical bonds contain a ton of potential energy, which is what we use to break down in order to release the energy to power our bodies. So food is full of chemical bonds. Kinetic energy is another definition. Kinetic energy refers to any energy of movement. So anything that's moving has kinetic energy. It's on display. So swimming is an example of kinetic energy. Water flowing over a dam, that's kinetic energy. When you're in the middle of releasing bonds, when you break bonds and it's releasing the energy, such as burning gasoline, that's kinetic energy. So these are pretty straightforward examples. So rollerblading, that's going to be kinetic. So anything with movement would be kinetic. Anything stored, such as a sandwich, that's potential. Mowing the lawn is kinetic. Gasoline in the gas tank, that is potential. Now, igniting the gasoline so it's on fire, then that would be kinetic. Just as we have kilometers to miles, that's metric to US, we also have two types of energy values depending on what part of the world you're in, as well as what type of scientists are studying. So we have joules, and J for joules, and we have calories. So chemists, they love using joules, whereas nutritionists, they love using calories. So these are interchangeable. 1 calorie is equal to 4.184 joules. Now, if I were to have the prefix kilo in front, that means 1,000. So 1 kilojoule is 1,000 joules. And then 1 kilocalorie, that's 1,000 calories. So this kind of gives you a overview of how much relative energy there is. So 10 to the 26th, I can't even imagine that, but that's how much energy is given off by the sun. Whereas 10 to the 5th is how much energy your body is giving off when you're sleeping. That I can't imagine. So here are more equalities. Here's the tricky part in the equalities. Whenever you have a capital C, that capital C means kilo. So capital C means kilo. So 1 capital C calories is 1,000 calories. In general, whenever you read some food label that says 48 calories, it's actually implied to be a capital C, and it's 48,000 actual calories. Crazy, I know. So make sure you understand these equalities and you're able to do a simple conversion. So for example, I could give you something like this. If you have capital C 10 calories, then that means there's actually 10,000 calories present. And that also means that there's going to be 41,184 joules that's going to be present. Or, another way to look at this is 41.184 kilojoules. Other definitions. To explain these definitions, I drew two pictures. In short, temperature is movement. So picture a car and it's moving. So there's the wind as the car is moving. I drew a Humvee when I meant to draw a car. I don't know why. But temperature is movement. So to the right, I drew a Star Trek Enterprise ship, and it's also moving through the stars. Why there's stuff behind there, I'm just trying to show movement. That's the stars. Okay. Anyways, let's move on. So, temperature is movement in chemistry land. Heat is the energy that powers the movement. So, picture gasoline in a Humvee. It probably gets like 3 miles a gallon, but there's going to be gasoline that's going to be present. So here I'm drawing gasoline, and that powers the movement of the vehicle. Using an even better analogy is the Star Trek Enterprise. It uses this inexhaustible, unlimited amount of energy called trilithium crystals. By the way, this substance is mythical. It doesn't exist in real life. If you try to draw trilithium, you'd violate the duet rule, just FYI. But bottom line is, in Star Trek fictional land, trilithium is unlimited energy. So, heat is energy that powers the movement, just as trilithium powers the movement of the Starship Enterprise nonstop. So the energy never gets degraded like gasoline gets degraded. Now let's apply those analogies to real world particles. So temperature is the total particle movement of a substance. So if I've got a bunch of particles right here, then it's any type of movement. Maybe the particle itself is moving in a single direction, or maybe the particle itself is vibrating. So that's my vibration symbols. But it's vibrating back and forth. It doesn't matter. Any type of particle movement is considered temperature. Let's go back to heat. Therefore, there's this invisible energy that we call heat. When a particle has it, it's inexhaustible. As long as the particle has this heat energy, it will power the movement of the particle until the heat energy is taken away. So here we see the heat energy. Now what exactly is it? Well, don't worry about it, just know that it exists. And it's energy that powers the movement of particles within a substance. Whenever we want to speed up the movement of particles, aka increase the temperature, then we need to go ahead and increase the amount of heat that's put in. Now please keep in mind that in chemistry land, heat is not like the term hot and cold like we use in day-to-day life. Heat is a chemistry term which means energy. So please keep that in mind. Now, we can quantify our temperature, and just as we have kilometers for the rest of the world and the US likes to use miles, we have the same issue with temperature units. We discussed this on the first week of lecture material. So Celsius is used by the rest of the world. That's considered a metric. Fahrenheit is used by the US, and then Kelvin is used predominantly by scientists, what they call International Scientific, or SI. It makes sense that it should have been IS, but they decided to switch it around. So, oh well. Now, Celsius, it goes by the freezing point and boiling point of water, so it has nice units that go from 0 to 100. And yes, you can have negative values because you can get below the freezing point of water. So you can have like negative 25, you can have negative 200 degrees Celsius. Fahrenheit, it's 0 is actually below the freezing point of water, and the boiling point of water, it goes up to 212. So because the values are so arbitrary for Fahrenheit, most people like to use Celsius because we have a nice 100 unit scale, and then serious scientists like to use Kelvin. Now, I do want to point out that Kelvin is absolute movement. Let me spell that again. Kelvin is absolute movement. So for example, if you are at 0 Kelvin, then there is no movement by any of the particles in a substance. It turns out pretty much every particle in the universe, even the coldest part of space, has some sort of that heat energy that powers a little bit of movement. So the coldest part of space that they've found still has a temperature of about 3 Kelvin for the particles that are in that area. It's super hard to get anything devoid of all of this heat energy that we're talking about. Scientists have been able to get down to like 0.1 Kelvin, 0.2, but it's very challenging. So you can go through those right there. It's very simple questions. Now we're going to get into temperature conversions. I want us to go straight to the very end of the slides. Just to give you a reference point, you'll be given questions like these right here. And then you're going to be asked to predict the final temperature from the starting temperature. You will need to memorize these temperature conversions right here in order to accomplish this. And you will apply these on future quizzes and exams. You want to notice that for Kelvin to Celsius and Celsius to Kelvin, these two equations may vary depending on professor and book. So some professors and books use 273.15. Other ones, like in the previous slide, use just 273. For the quiz and exam, go ahead and use the one with 273.15. I am going to be teaching you to answer these with proper sig figs and going through the sig fig rules on these as well. Now you won't have to worry about deriving them if you already have them memorized. So in this equation, we go from our starting Celsius to Fahrenheit. Fahrenheit to Celsius. And here's a problem that we can practice using these. Once you have these memorized, it's just simply plug and chug. The hard part is figuring out the proper sig figs, which is what I'm going to emphasize now. So a person with hypothermia has a body temperature of 34.8 degrees Celsius. That's pretty cold. What is the temperature in Fahrenheit? So we identify the proper equation that we need to go. In this case, it's going to be from Celsius to Fahrenheit. Your starting values in the equation, you can assume all of these are going to be non-measured. All of them are non-measured. Now, whenever you see the word exact in my slides, you can cross it out if you want, and you can say non-measured. And as we learned, non-measured have infinite number of sig figs. So the 1.8, that is non-measured, and it has infinite number of sig figs. So you plug in your starting value into the proper equation, 34.8. Starting values inside the question is always going to be measured. So in this case, we have 3 sig figs. We then have a combination of multiplication and addition in this problem. So therefore, we have different types of sig fig rules. So when you're multiplying, then it's going to be by least sig figs. So in this case, 3 sig figs, this is infinity. So the intermediate value is going to have 3 sig figs. Now that we're adding, it's going to go by least decimal places. So in this case, we have 1 decimal place. For 32, because it's non-measured, it has infinite decimal places, so hypothetically the zeros can go on forever because it's non-measured. So we have 1 versus infinity decimal places, so it should be rounded to 1 decimal place. Once we have our final answer with the proper decimal places, then we can go back and go, okay, now the final answer has 3 sig figs. Here's another problem going from Fahrenheit to Celsius. In this case, we're going to go ahead and plug in our 105.8. Please keep in mind that all of the values inside the equation, all of these are non-measured. So they have infinite number of sig figs for each of these values. The starting value in the question will always be measured. So in this case, there's 4 sig figs. Notice we're doing subtraction, so we're going to be looking at the number of decimal places. So in this case, 1 decimal place, and we have infinite decimal places for 32. So here is your intermediate value. So with least decimal places, we have 1 decimal place. Now we're doing a division, and now we're going back to least sig figs. So here we have 3 sig figs. We have infinite sig figs, so it should be rounded to 3 sig figs. So here's another problem you can go through using proper sig fig rules. Yes, you can have negative values, obviously, because you can get colder than the freezing point of water for Celsius and Fahrenheit. So therefore, you'll have negative values you have to work with. So make sure you know how to input negative values on your calculator. You can't press the minus. There should be some sort of special plus minus button on your calculator. So don't just try to use a minus, regular minus, like you're subtracting. Use the special plus minus, otherwise that might give you the wrong answer. Starting value has 2 sig figs. And here is the worked out problem. So 2 sig figs, infinity. There's our intermediate answer with 2 sig figs. Now we're going to add it together, least decimal places. Notice there are no decimal places on my intermediate value, so it should be rounded to no decimal places for your final answer. Again, be sure to use the proper sign key on your calculator. And then we can convert to a Kelvin. Please keep in mind that there are multiple equations for converting from Celsius to Kelvin and Kelvin to Celsius. We're going to use 273 without the 0.15 for this example right here. So in this case, 37 degrees Celsius plus 273, that's going to go ahead and give you 310 Kelvin. Notice there are no decimal places, because your starting value had no decimal places. Now, here's an interesting thing. Hypothetically, if I use the other equation where I had the 273.15 that we see here, I would have had an intermediate answer of 37.15. However, the 273.15 is non-measured. It has infinite sig figs or infinite decimal places, so you can think of it as the zeros going on forever. So this still would have had to been rounded to, instead of having an answer that is 310.15, I don't know why I wrote down 37, ignore that, 310.15, because there's no decimal places, the final answer would have still been 310 without any values to the right of the decimal place. So 310 Kelvin. Now some of these can be tricky because you could be asked to go from Fahrenheit to Celsius or Celsius to Kelvin, so you have to apply the proper calculation. In my opinion, the trickiest one to do is 367 Kelvin to Fahrenheit, because here you have to go from Kelvin to Celsius and then Celsius to Fahrenheit. Here is a worked out problem to the side for 367 Kelvin to Fahrenheit. First thing, we need to convert from Kelvin to Celsius. So I had to use, let's see, oops, wrong one. I have to use the bottom one. Keep in mind that the starting value has no decimal places, so your intermediate value should have no decimal places for the Celsius. You then have to plug it in. Notice when we do multiplication, it's these sig figs. So the intermediate value should have 2 sig figs. Now the original one was 169.2 calculation, but because we're keeping the first 2 sig figs, we have to round from 169 to 170, where 0 is a placeholder. We then add it together, least decimal places, and that gives you your final answer. So try messing with those. Those are pretty cool. Now we're going to go ahead and start energy part 2. We're going to investigate heat transfer and specific heat. Here's the first slide for energy and matter. It's packet 7 and it's part 2. Going back to my Star Trek analogy, let's see, there's my Starship Enterprise again. And then this Starship Enterprise, the movement is powered by this unlimited resource called trilithium crystals. Now, in discussing transfer of energy, let's go ahead and come up with a scenario. So let's pretend that there is this jellyfish-looking alien spacecraft, and as the Starship Enterprise is flying through space, the jellyfishmen decided to steal the trilithium crystals. So it steals the energy source. Now when it steals the energy source, then that means the Enterprise will have no energy for movement, and it completely stops. and then the alien aircraft flies away. So, using this as a starting point, let's pretend we have a whole bunch of particles and they have the heat energy that we talk about. And instead of writing out the word heat, I'm just going to use H. And H is used for that heat energy. It's energy that powers the movement of particles. When there's another substance that comes into contact, so I'm just going to call this substance B. When it comes into contact, there it is right there, then the heat energy is going to transfer over. Now please keep in mind the heat energy is always constant. It's like the trilithium crystals. It's inexhaustible. It will always power the movement of particles. However, it's very easy for it to be transferred over and stolen by another particle. Now that particle, once it contains the heat energy, then it can go ahead and start moving around. It has movement. And then the original particle, it'll stop moving, so to speak. So because we transferred the energy, then the fancy name for this in chemistry land is, go figure, heat transfer. Heat transfer. Heat transfer. That took me forever to draw the Enterprise, by the way. Just thought I'd share. In this example to the left, I have my hand, and my hand is full of that heat energy. And what's going to happen is, as I hold a copper penny, it's going to be transferred into the copper penny. And then the particles are going to go ahead and start moving, such as vibrating. Now let's go ahead and relate temperature back to movement. Temperature is the sum movement of particles within a substance. So as I hold the copper penny, that heat energy is going to transfer into as I hold the copper penny, the heat energy is going to transfer from my hand to the copper penny. And using this table right here, the longer I hold it, then the higher the temperature will go up, from 76, 77, 78, 79, and so forth. Now over here is another hand holding water, and the same thing will occur. The heat energy will transfer from my hand into the water, and then it's going to go ahead and start raising in temperature. Now we're going to get into the concept called specific heat during heat transfer. There is a specific or quantitative amount of heat energy that is always transferred before the temperature rises. So for example, there requires it requires 1 unit of joule energy for the temperature of the copper penny to raise in temperature. So if I add in 2 joules, then it'll go from 76 to 77 degrees Celsius. If I add in 3 joules, it'll go from 76 to 78 degrees Celsius. So notice it requires a specific amount of energy, in this case 1 joule, for it to raise in temperature. So the amount of energy required to raise the temperature, specifically raise the temperature, is called specific heat. In general, 1 joule of energy is required to raise the temperature 1 degree Celsius for an amount of 1 gram of that substance. Now compare the specific heat of copper penny to the specific heat of water. It turns out in order to raise the temperature of water, you are required to specifically put in 4 joules of heat energy. And then you will have a 1 degree temperature change per 1 gram of that substance. So for example, holding the water in my hand, after I put in 1, 2, 3, 4 joules of energy, then the temperature will rise from 76 to 77. And another 4 joules from 77 to 78. Now let's compare the numbers. Because water requires a higher specific amount of heat energy, then we say it has a high specific heat. On the other hand, because relative to water, the copper penny required a low specific amount of heat energy, we say it has a low specific heat. So understand the relative terms of low and specific heat. It turns out for substances with low specific heat, it requires low amounts of heat to increase in temperature. And low amounts of heat are given off when decreasing, as opposed to high specific heat, which requires a high amount of heat energy to increase in temperature. Now let's go to speed. How long does it take? What's the time it takes for it to gain in temperature or lose in temperature? It turns out that the higher the specific heat, then the more joules of energy required. So therefore, it's going to take longer for a substance with high specific heat to increase in temperature, because it has to put in all of those joules of energy in for it to raise in temperature. Whereas substances that have a low specific heat, such as copper penny, it's actually pretty quick. And it can change in temperature very quickly because it doesn't require that many joules of energy for it to be put in, for it to increase, or that many joules of energy to be taken out for it to decrease. So here we have to apply the concept of low and high specific heat. Ocean water has a high specific heat, so therefore it's going to go ahead and be pretty slow in changing temperature because there's a lot of energy that needs to change. The surrounding air, as the temperature cools, because it's going to transfer the heat energy into the surrounding air is going to warm up. Sand in the desert is hot in the day and cool at night. So in this instance, sand has a low specific heat, and because it has a low specific heat, it very quickly gives off its energy and changes in temperature, as opposed to very quickly gains the energy. So it gets very hot during the day and gets very cool at night. So if you have to live near one place, it's better to live near the beach, because the ocean, because of its high specific heat, it helps moderate the temperature, because there's so much energy that needs to be transferred for any temperature changes in the ocean. Then the climate around the ocean area tends to be pretty moderate. Compare that to living in the desert, where low specific heat and the temperature is going to change very quickly. So it gets really cold at night and very hot during the day. So those are the answers. Now we're going to get into quantitative. Quantitative is when we actually do calculations. We're going to actually calculate the specific heat for a substance. And every substance has its own unique specific heat. This is actually pretty easy. You don't have to do much reasoning out. You simply have to plug and chug your given joules, grams, and the temperature change. The temperature change is probably the hardest. It's always going to be temperature final minus temperature initial. But if you've already mastered temperature conversions, where you just have to simply choose the correct equation and plug and chug it, then this is going to be pretty easy for you. So first off, memorize the specific heat equation. It'll be energy on top divided by grams times Celsius. Next, memorize the alternate form. The alternate form is going to be calories divided by grams times the temperature change in Celsius. Also make a little comment here that whenever we have Celsius, that actually means temperature final minus temperature initial. Here's a worked out problem. First off, we're starting off in joules. There's the grams that absorbs the energy, and the temperature rises from 20.2 Celsius to 24.5 degrees Celsius. So here's our specific heat equation. Again, this is pretty straightforward. You simply have to plug and chug. So in this case, we have joules, and that's going to be plugged into the joules unit. And then we have grams. Grams is going to be plugged into the grams unit. And then we have temperature change. Now here's the hard part. You're going to have to do temperature final minus temperature initial. So here is the temperature final minus temperature initial, and you have to make sure you put in this value and note whether it's positive or negative. So right now this is actually positive, so that's a positive value. If it, we always like to write these as positive, so all the questions I'll give you will be positive, so you don't have to worry about that. So it's going to be 4.3. You then go ahead and do your calculation. Keep in mind we have to worry about sig figs. So 3 sig figs on top, 3 on the bottom, 2, so it should be rounded to 2 sig figs. And here is your final answer with the appropriate units. So make sure you memorize and know the calculation for it, both for joules and for calories. Now I'm going to go ahead and skip to slide 7. This is a heat transfer equation. Again, you want to memorize this equation right here. Now this equation is used to calculate the transfer of heat energy. So it's quantitative, it's the actual values. So before we just kind of reasoned it out. Now we're trying to get some actual numerical data. So let me go ahead and set up the context of what type of instrument we would use. We might use something called a coffee cup calorimeter. And in some of our later science courses, you definitely will be doing this type in lab. So it literally is a coffee cup, insulated with a cap on top. And inside we have our substance with water that is surrounding it. So the substance is immersed in water. And then we have a thermometer right there. So this is called a calorimeter because it allows us to calculate out the transfer of energy using the change in temperature. Now there's many scenarios, but I'm just going to have you focus on one. We're assuming that we're going to have some sort of substance in there that's going to transfer its heat energy into the water itself. And then the water will go ahead and change in temperature. Now there's actually 2 ways we could transfer it. We could have the heat energy transfer out from the substance into water, or let's assume that we have a substance that's really cold. We can have water transfer its heat energy into the foreign substance, such as a metal block. Bottom line is, if we have a sample transfer its heat energy into the water, then the temperature is going to rise. Because temperature powers movement, and because the water is picking up the heat energy, then the temperature will rise. And so when we do our temperature final minus initial, we're going to have a positive value. Now, on the other hand, we could have a situation like this, where the heat energy is transferring into the block, in which case it's the water is going to start to cool. And then when we look at our temperature final minus our temperature initial, then it's going to be a negative value. So let's go ahead and go straight to an actual calculation so you could see it in work, or see it in action. I'll give you an equation that looks like this. How many kilojoules, that's energy, are needed to raise the temperature of 325 grams of water from 15 degrees Celsius to 77 degrees Celsius? Okay. So, first thing we need to do is do the temperature final minus initial, and that's 62.0 degrees Celsius. Again, this is a plug and chug type of problem. So having memorized this, we're going to plug in our value from the temperature final minus temperature initial. Please keep in mind proper sig figs is required, so at least decimal places. And then I need to plug in the grams, and then I will give you the supplied specific heat. So there is the temperature change that's put in there. There's the grams, and then here is the supplied specific heat. By the way, for these temperature conversions, I have to give you the specific heat. It will be given for these type of problems. Now this one's made to be a little bit more challenging. Not only do you have to go from joules, but you have to go from joules to kilojoules. So you'll notice that everything should cross cancel out. The grams, the Celsius, and then the specific heat, grams and Celsius, should cancel out, leaving joules. This allows you to immediately convert from joules to kilojoules. So let's do another problem. And oh, by the way, make sure you report whether it's positive or negative. Here's the next problem. What is specific heat for a substance which requires the absorption of 2,000 calories to raise the temperature of 23.03 grams to from 23.51 Celsius to 91.04. Now, given a problem like this, you have two equations that you've memorized. So either this one right here, that's the heat transfer equation, or this one right here, the specific heat equation. And there's two forms, one with joules or one with calories. So you have to apply the proper equation. So in this case, we're going to have to use the specific heat equation, and we'll use the calories over grams times the temperature change Celsius. So I solve for temperature final minus temperature initial. Next, I went ahead and I set up my my equation. Calories are on top, divided by grams, divided by the change in temperature. Now I'm just going to go ahead and solve the problem. This gives us 1.364 calories over grams divided by Celsius. Now all of these values are measured, so it should be 2, 4 sig figs. Let's go ahead and move on to the next problem. This one's already worked out for you. Again, you're given a problem like this and you have to figure out which equation to use. So you'll either use a heat transfer equation or you'll use the specific heat equation. So in this case, a big hint is that we already gave you the specific heat, so that's a big hint that it's a heat transfer equation. So you have to do the temperature final minus temperature initial. You then have to go ahead and plug that in, put in the grams, and then put in the specific heat. You know you've done it correctly if everything cross cancels, leaving the desired energy value. So in this case, it's going to be in calories. Now, we have a new concept that we're about to get into, and this concept has to do with positives and negatives determining whether energy is going in or energy is going out. So in short, for heat transfer results, if the value reported is a positive value, then we can assume that energy is going in to a substance. If the value is negative, then energy is leaving the substance. Energy is going out. So in this case, if I have something like this, 248 joules, then it's implied that energy is leaving. It's coming out. If I have something like this, 25 calories, then energy is going into it. Now, using that concept, if energy, let's say I have substance X, and energy is going out, then substance X is getting colder. Because without the energy, then the temperature is dropping. On the other hand, if I have substance Z, and I have energy that's going in, then the substance is getting warmer. Keep in mind that heat energy powers movement of particles. So the more heat energy you have, then the higher the temperature. So in this case, it's a negative value, and energy is going out. Also keep in mind that all of these are measured values, so the 8.9 has 2 sig figs, so your final answer should be rounded to 2 sig figs. Now we're going to get into collision theory, and now you get to really see my artistry. So, in collision theory, chemical reactions occur due to incoming atoms colliding against each other. In a chemical reaction, we see molecules bouncing around like billiard balls on a billiard table. And then when they hit other molecules, the collision force, or what's called the activation energy, will cause bond breaking and then bond making. So the blue represents N2, the red represents O2, and after colliding, then bond breaking and bond making will occur. Back to the analogy I keep talking about. Here we have cars coming in, and when the cars hit each other, they collide. And it's that collision energy which results in the braking of the cars, and maybe if they hit hard enough, then maybe they may fuse together. Ironically, my poor drawing skills has resulted in what looks like a realistic car wreck. So here's another example. We have two particles, particle A, particle B. For a chemical reaction to occur, they have to slam against each other, and bam! A reaction occurs. Now, we like to go ahead and use a potential energy diagram to show the changes in energy that occur. So, for example, I'm going to go ahead and draw it like this right here. My starting particles, here's before they reacted. So that's particle A, that's particle B, and then when they hit each other, bam! The energy from the collision caused bond breaking and bond making to occur. So, bam! And that results in this case, the formation of an AB molecule. Now we have another term for collision energy, and that's called activation energy. And it's the amount of energy required to activate a chemical reaction. And it's the energy from the starting point of the reactants to the end point during the collision. Now that point that they collide, we have another term for that, and that's called transition state. So be sure you're able to label the activation energy and transition state, resulting in the new products that are formed afterwards. So here is N2 and O2. And I'll go ahead and I'll try to color code this. There's my O2 reactant. Here's my N2 reactant. This is the potential energy diagram. And then here is the N2 and the O2 as they've just collided. And then here is your final products. Where we have two molecules of NO, also known as nitrogen monoxide or nitrous oxide. Now let's go back to the potential energy diagram. On the x-axis, we have the reaction progress over time, also known as reaction coordinate. Got a weird name. And so at the beginning of the reaction progress, we have the reactants, and at the very end we have the products. And then the point at which they collide we call the transition state. And the amount of energy required to activate the chemical reaction we call the activation energy. And that comes from the energy of the colliding particles. And the potential energy, that's the amount of stored energy. So that's the level for the stored energy. And it turns out it takes a lot of energy in order to start the chemical reaction, and that comes from the colliding of the particles. And then as the bonds are started to form, then a lot of energy is released, and that's energy out. Now, I do want to point out, I drew this in two different ways. You may not have noticed this. I can either draw it like this, where the product potential energy is lower than the starting reactant potential energy, in which case we call this a exothermic reaction, because there's a lot more energy that's exiting than required for the reaction. On the other hand, I could have, writing in the right-hand corner, potential energy diagram that looks like this. And in this one, there's a lot more energy going in the reaction than there is coming out. So you can see the potential energy of the reactants is lower than the energy of the final products. So we say that this is a endothermic reaction. So a lot more energy is required to go in than is released. So this is an example of a potential energy diagram that is endothermic. So you should be able to recognize that. Now we have another term. Instead of saying heat energy all the time, or just saying heat, we have another term for this. We call this enthalpy. Enthalpy is just another way of saying heat. And we came up with the term enthalpy because people kept getting confused between the term heat, referring to energy, and heat as in hot and cold. Now, oftentimes when we figure out whether this is an exothermic or endothermic reaction, we go ahead and take the products minus the enthalpy of the reactants. And this gives us the change in enthalpy. So that is the change in enthalpy. Now, if the change in enthalpy is positive, then it's going to be endothermic. If the change in enthalpy is negative, it's going to be exothermic. So endothermic means requires a lot more energy to go into the reaction, as exothermic means a lot more energy is coming out. So a good example of an exothermic chemical reaction is the combustion of methane or natural gas with oxygen. There's a lot more energy that is being released, and so that energy that's being released will then result in various types of very active gases that are formed. Yep, that's it. So another way I can write that same type of reaction as exothermic or endothermic is to go ahead and place the term energy or heat on the right side or the left side of the chemical equation. And so that's a exothermic chemical reaction. So let's go ahead and summarize some of the things I talked about. The top portion is for exothermic reactions. The bottom portion is for endothermic reactions. Here is a chemical reaction. This is with charcoal and hydrogen gas, and that creates methane. And then here is energy that's being released. So let's go ahead and focus on whether this is exothermic or endothermic. Here is your chemical reaction. If the energy value is on the right side, then it's considered exothermic. If the energy value for the bottom one is on the left side, it's considered endothermic, because energy requires to go into the reaction. So you'll be asked to classify exothermic or endothermic based on a given equation along with the location of the energy values. I could also give you a potential energy diagram. Notice how the final product portion of the potential energy diagram is lower than the reactant, so therefore it's exothermic. Whereas in the bottom one, the product is at a higher potential energy than the reactant. And so in this shape, this is considered an endothermic, because a lot more energy is required to go in. And then finally, going back to that new term, change in enthalpy, if you see a negative value, automatically it's considered exothermic. But if you see a change of energy that's positive, it's considered endothermic. So you're going to be asked to recognize whether it's going to be exothermic or whether it's going to be endothermic. So here are some types of questions I could ask you. This is the chemical reaction based. Notice how the energy is on the right hand side, so therefore it's exothermic. Whereas in this one, the energy is on the left hand side, so it's endothermic. Now we're going to start getting into reaction rates. And this is the speed of reactions. So reaction rate is the speed of reactions. Some reactions are really fast, other reactions are really slow. So one of the slowest reaction is the decomposition of plastic. It takes thousands and thousands of years for plastic to decompose. So it has a slow reaction rate. A fast reaction rate was the one I just talked about for combustion reactions. So this one right here, this has a very fast reaction. So charcoal and hydrogen gas will form methane and release a lot of energy. And reactions that have a fast reaction rate and release a lot of energy really quick, we have another term for those, and that's called explosion. So reaction rates are really important. We need to know how fast the reactions occur. Now, things get really complicated. So first thing I'm going to go ahead and do is I'm going to show you another diagram. On the y-axis, we have the amount of products. On the x-axis, we have time. So in your initial reaction rate, there's very low amounts of products because the reaction is just starting. However, as time goes along, a lot more products start to form. Now, at some point, you start to run out of reactants, and then there's a nice plateau where no more products are formed, just because you've ran out of reactants. And then sometimes the products can change their mind and become reactants again. So what we're going to do is we're only going to focus on the very beginning of a chemical reaction. So the beginning only. And so we call these the initial reaction rate because we're just focusing on the beginning. So focusing on the beginning, we're going to figure out the factors that affect the initial reaction rate as well as ways to increase the reaction rate. And there's different ways we can do it. We can look at temperature, we can look at the orientation of colliding molecules, and the concentration. So these are the factors that affect the initial reaction rate. And yes, we're going back to the car analogy. So think of chemical reactions as freeway traffic collisions. So here is my freeway. There's 3 lanes. Um, in short, a factor that would affect collisions in a freeway is the concentration. So that's the number of cars that are present. Now, if it's rush hour time, the more cars you have, those are all supposed to be cars. Just go with it. Then there's a greater chance that there's going to be more accidents. Ergo, if there's a higher concentration, then there's going to be more chance for reactions to occur. Now, an odd thing occurs when you have a freeway collision. Usually when you have collisions, you may have a bottleneck, and then there will be less cars that are in front. And with less cars in front, then there's less of a chance for future car accidents to occur after the main car accident occurred. So the same thing happens with chemical reactions. When you start to run out of the initial reactants, then there's going to be less chemical reactions. The next type of chemical, or the next analogy I want to look at is orientation. If you truly wanted a hideous car accident, one of the worst types of accidents are when you do what's called a T-bone. And that's where the car hits the side of the other car. And that's where it causes a lot of damage. On the other hand, if you were just to have what's called a, there's my car, if you just were to have a bumper to bumper collision, then there's going to be less damage. So the what we call the orientation makes a big deal about the severity of a car accident. And the same thing happens with molecules. So for example, if I were to have these two molecules, oxygen and nitrogen gas, to hit each other at this particular angle, there's going to be a low amount of chemical reactions occurring because they're at the wrong angle. This angle that they're going to hit each other, where the oxygen hits the nitrogen at this angle, it's like doing a bumper to bumper. Now, if I were to have them molecules on the side, like this right here, and then they hit each other, then there's going to be a high reaction occurs because the atoms are aligned just perfectly to maximize bond breaking and bond making. So that's orientation. So we talked about the concentration, and my slides talk about collision frequency. We talked about orientation, collision geometry. So here's another example for NO2, or nitrous oxide, or nitrogen monoxide, and this is ozone. For them to react, they have to hit at the right orientation, or what's known as collision geometry, for a reaction to occur. So that's good. This one over here, that's bad, because it's hitting at the wrong angle. Now let's hit the last one. This is collision energy. The molecules must collide with enough energy to form bonds. So going back to my car analogy, if you really want a strong accident, and by the way, I do not want anybody to get into accidents. This is just an analogy, and this is just really generic, so FYI. Then one thing you can go ahead and do is increase the speed. And with a higher speed, then that's going to result in a greater accident. Well, collision energy also relies on the speed of molecules. So for example, if I have molecule A and I have molecule B, it requires a high speed, and the magic word for speed in chemistry land is temperature. So that's the sum movement of the particles of the substance. And so when they hit each other at a high velocity due to temperature, then that most likely it will achieve the collision energy. And let's go back to our potential energy diagram. So there's potential energy, and then there's my two particles, and they have to hit each other with enough energy in order to go up to that transition state. And another name for collision energy is activation energy. And then a reaction can occur. You are responsible, even though I got into great detail. I'm going to ask that you are just vaguely familiar with these ideas and absolutely memorize these three factors that affect initial reaction rate. Please also memorize this word affect, because on a future quiz or exam I could say what are the three factors that affect an initial reaction rate, or select the three factors that affect the initial reaction rate. Now compare that to increasing the reaction rate. So effect, we just talked about the general circumstances for increasing initial reaction rate. These are the three factors that actually increase them. The first one is reactant concentration. So just with the car analogy, the more cars you have, the more likely you're going to get into an accident. The greater the concentration, the more likely there's going to be a chemical reaction occurs. Reaction temperature. So if you heat up or you increase the temperature of the solution that the reaction is occurring in, then you'll increase the reaction rate. And then the last one is called a catalyst. So a catalyst is when you actually add a special chemical and it's not part of the product. So in my example right here, I'll have a reactant here, a reactant here. Over here I'll have my product. If there's not enough energy for it to go all the way up to the top of the transition state, by adding in this mysterious catalyst molecules, we can actually lower the activation energy. We can lower the activation energy. It does this by optimizing collision alignment. So for example, and this is just a general example, let's say I have hydrogen and chloride, and the chloride needs to have its unpaired electrons, I'll just do it like this, unpaired electrons facing each other just right for a reaction to occur. If they're in the wrong alignment, so the electron's down here and the chlorine's on the other side, then there'll be no reaction. Or it will require a lot more energy for the reaction to occur. So what a catalyst does is it optimizes the collision alignment. Think of a Pac-Man where it holds one of the reactants in its mouth, so that way the other reactant can go ahead and optimize its collision. So memorize this statement right here, because I could ask you a general concept question on it. A catalyst lowers the activation energy by optimizing the alignment of colliding reactants. So please have these three factors for increasing, and make sure you can distinguish increasing with affecting. Three factors that increase: concentration, temperature, and addition of a catalyst. So let's go ahead and see these factors, the three factors that affect initial reaction rates and the three factors that increase the reaction rate in an actual simulation. So here I have two reactants, and again they have to hit each other at the right angle with enough energy for a reaction to occur. Obviously, this initial reaction rate is going to take a while. So now I'm going to go ahead and increase the reactant concentration. So in the left-hand corner, where my mouse mouse cursor is, I have 12 reactants, and I'm going to go ahead and play the simulation again. And now there's a greater collision frequency, and you can start to see the products start to form. So now there's 2 products. And as time goes along, the number of products will start to increase. So now there's 4 products. Now let's go ahead and look at energy, collision energy. And one of the ways that we can go ahead and increase collision energy is by increasing the temperature. So I'm changing the temperature from 100 to 200. And let's see how fast the molecules move now. So now they're moving at a faster rate. This increases actually the frequency of collisions, as well as the collision energy required for the reaction, aka activation energy. So notice how there's now 8 products that have formed. So now I'm going to go ahead, keep the concentration roughly the same. I'll lower the temperature to what it was, or around what it was before. And I'm going to add in a catalyst. So we talked about how you need the proper collision geometry, the proper orientation for a reaction to occur. And so I'm going to go ahead and add in a catalyst. So those are the catalysts, and their goal is to go ahead and scoop up reactants and optimize the collision alignment. Now let's see how fast the reaction occurs now. So I've lowered the temperature. However, with the catalyst, you'll notice that already 8 products have formed. So it greatly speeds up the initial reaction rates. Let's see that again, because that was kind of cool. We can do multiple things. We can increase the concentration, we can increase the temperature, and we can maximize the reactant concentration and catalyst, and watch at how many products are formed. Now, your body is filled with catalysts called enzymes. All of our natural biological reactions take forever to do, and we would die unless we had these catalyst enzymes in our body. And the catalyst enzymes in our body increase reactions to a point that keeps us alive. So back to the slides. Make sure you're able to answer these type of questions, and you know the 3 factors for affecting and increasing reaction rates. And then here are various scenarios that I could test you on. Raising the temperature, that increases it. Adding O2, which is a concentration of reactants, increasing that concentration increases it. Adding a catalyst definitely increases it. Lowering the temperature decreases it. Here is a summary. So this is for increasing, again, increasing reaction rates. So here are the factors, here are the reasons why. So make sure you have those concepts down. Now it's going to get a little bit easier. We're going to talk about the three main states of matter: solid, liquid, and gas. Pretty straightforward. Now there are other exotic phases that we are not going to get into. So there's something called plasma, for example. The sun exists in a plasma state, but we're not going to get into that. We'll just stick with the three. So solids have a, make sure you have these down, although these should all be common sense, so not a lot of studying needed. They have a definite shape, a fixed shape, and a fixed volume. Solids are made up of particles, and they're in a fixed arrangement. Now, most people think because it's a solid, it's not moving. Yes, particles, all particles move. Instead, what's happening is they're vibrating, but technically they're still moving. Liquids have a flexible or indefinite shape, indefinite volume, and then the particles in a liquid, they like to be mobile, where they'll move around each other. They won't fly off into oblivion, they'll just move around each other, so they're mobile. Gases do not have a shape, they do not have a volume, so it's indefinite. And unless there's a container, gas particles will fly off in various directions. So that's why all gases need a container. Or if you're on planet Earth, for those lucky people, gas particles can rely on gravity, so G for gravity, to make sure the particles don't fly off and keep it close to Earth. So some other external force. So solid, liquid, and gas. Usually we use S for solid, L for liquid, G for gas. Make sure you know the three states. And another word for state is phase. So that means the same thing. And then don't forget, even though you may have a solid, the particles are still moving, they're vibrating. So it's very slow. So you can go through those questions. Now we're going to get into changes of state. So the snowman is a solid. The melted snowman is a liquid, and then you have gas. You're going to need to memorize the 6 changes of state. Some of them are common sense, other ones are not. So, to go from a solid to liquid, it's melting. And to go from a liquid to a gas, it's called vaporization. And there's 2 types of vaporization. There's evaporation and boiling. And we'll get into that later. And then the opposite way is melting to freezing. Or you can do gas to liquid. That's condensation. Now, there's some exotic ones, or exotic changes of state. Sublimation, that's when you go directly from a solid to gas. So if you've ever messed around with dry ice, it goes immediately from a solid to a gas. And then there's gas to a solid. Oftentimes when we're putting on coatings, metal coatings, we have a special room where we have gaseous metal, and then it's deposited on the surface for metallic coatings. So that's deposition. And then make sure you have those down. In addition, you also want to keep in mind whether heat is being absorbed, heat's going in, or heat is being released. So I've color-coded this. Make sure you have each of these changes of state memorized with heat absorbed and heat released. So for example, to go from a solid to a liquid, it requires that you have heat or enthalpy going in, and that makes the particles move. And the same thing, if you want the particles to move even further, you need to have heat or enthalpy going in. Conversely, if you want the particles to slow down, you need to take heat out. So enthalpy needs to leave, the energy needs to leave, going from a gas to a liquid. And that's heat is released. And then the same thing from a liquid to a solid. Enthalpy needs to leave, so heat is released. So make sure you know the 6 changes along with whether heat is absorbed and released. And then this gives you examples. Now it is possible to do calculations to figure out how much energy is required to change a substance, for example, from a solid to a liquid. The exact number in order to melt it or to release the energy in order to freeze it, we call the heat of fusion. I'm not going to ask you calculations. I am going to ask you about the concept. So concept only. Well, that got messy. Concept only. So here's a calculation for heat of fusion. If you take more science class, then you'll be getting into these calculations, but I won't be testing you on those. And then here's sublimation, condensation. So if you ever blow on a mirror and you see liquid form, that's because hot gas from your breath forms liquid on the surface, and they call that condensation. Now, vaporization is when we're going to go from a liquid to a gas, and there's 2 types, evaporation and boiling. Now, I just need you to be familiar with the definitions for evaporation and boiling. Definitely know the concepts. So let's go ahead and take you into boiling first. So on slide 40, you see an example of boiling. Essentially, when you're at or above 100 degrees Celsius, then random parts of a liquid will go ahead and form gas particles. Now, all the energy that goes into the water, it'll go ahead and convert just random parts from liquid to gas, and then the gas bubbles start to rise, and then they leave, and then they give off, in this example, gaseous water particles. Now, honestly, you can't see, for the record, you can't see gaseous water. You can only see floating liquid droplets. And clouds are actually a mixture of liquid and solids, but true gas you can't see. Also known as the term water vapor, that's just gaseous molecules and you can't see it. But I digress. So at 100 degrees, random parts will form gas. Evaporation is when you're below the boiling point. And it turns out there is energy that is, so here's my Bunsen burner. There's energy or heat that's going in. Only it's below 70 degrees Celsius. Now evaporation occurs all the time. The energy from being in a room will evaporate spilled water on a counter, for example, or the sun will evaporate water outside. But in this example, I'm just using a Bunsen burner. But if it's less than 70 degrees, then the best example to explain evaporation is to look at a game called Red Rover. Now in Red Rover, we have somebody that wants to go ahead and try to break through a barrier. And if they're deeply inside a group of people, they're going to have trouble getting through. So same thing with water molecules. Even though they've been energized by the heat, they just don't have enough energy to be turned into gaseous molecules. However, on the surface, or the line for Red Rover, if one of the people on the line decides to go ahead and make a break for it, he is surrounded by less people to hold him back, and the person playing Red Rover can go ahead and leave. Same thing with evaporation. It's the surface water molecules that are less surrounded by other molecules, and they're able to escape. And what happens is in evaporation, it's the surface molecules that will turn into a gas one layer at a time. So that top layer will go ahead and escape, and then finally it will expose the next layer, and those molecules will escape, and then the water level line will slowly go down as water molecules are released one layer at a time. So in boiling, all the molecules have enough energy to form a gas, resulting in multiple bubbles, whereas evaporation, when molecules on the surface, be sure to circle that word, have enough energy to form a gas. Heat of vaporization. So this is another math compound unit that allows us to figure out the energy to go from a liquid to a gas or vice versa. Again, we're not testing you on the math on this, just on the concept. And let's get into and finish this up with heating curves. Heating and cooling curves. So here is solid ice, and it's below 20 degrees Celsius. As I start to heat up the ice, the temperature rises, so all the energy goes into increasing the temperature. But here's a cool thing. As soon as you get to the melting point, the temperature stops rising. It plateaus. And that's because all the energy, or the heat of fusion, all the energy goes into melting. When everything is melted, then the temperature will start to increase again. And temperature is movement, so the particles are moving faster and faster, and then boom, the substance hits another plateau, and the temperature stops rising. Why? Because all of the energy goes into making the water from a liquid to a gas, change of state. For example, boiling. And then after everything is a gas, then the temperature will continue to increase. So we call this a heating curve. A heating curve. So here's an example of a solid, such as solid ice. Again, there is some movement. It's vibrating. And I'm going to gradually increase the temperature. As I do that, it'll start to turn into a liquid. You'll see some particles as it goes from a liquid to a gas, or vaporization, that occurs. So here it is, a liquid, as the atoms are mobile and they're moving around each other. And then we have some vaporization occurring, but they're rotating around each other. So it's got an indefinite shape. And now this is a gas.